In this lecture, I'm going to be talking about another approach, another way that we can improve state-of-the-art models using contrastive learning. Because contrastive learning, you can use it. 85% of the articles are about unsupervised learning, and the rest of that is for supervised learning. Because originally it was suggested in the unsupervised setting. So we want to improve transfer and robustness of supervised contrastive learning. An ideal learned representation should display transferability and robustness. Supervised contrastive learning is promising for training accurate models, but produces representations that do not capture these properties due to class collapse. When all points in a class map to the same representations, and recent work suggests that spreading out these representations improve them, but the precise mechanism is poorly understood. We argue that creating spread alone is insufficient for better representation, since spread is invariant to permutation within classes. And instead, both the correct degree of spread and a mechanism for breaking this invariance are necessary. We first prove that adding a weighted class conditional info and CE loss to controls the degree of spread. We add a weighted info and CE loss. Then we studied three mechanisms to break permutation invariance using a constraint encoder, adding a class conditional autoencoder, and using data augmentation. There are two key challenges to achieve better representations. On the left, you see that the first challenge is balancing multiple contrastive loss terms with competing geometries. And we show that adding a weighted class conditional info and CE can balance the geometries and induce spread in the representation geometry. And in the right picture, the right one, the second challenge is that representation geometries may be invariant to class fixing permutations. The two examples shown both have a spread, but vastly different codes to find transfer performance. We analyzed three mechanisms for addressing this challenge: constraining the encoder, adding a class conditional autoencoder, and using data augmentation. The first challenge, which is balancing the spread, we first prove a simple result that a class collapse representation cannot have good transfer performance, which motivates spread. We then analyze whether loss of spread, a loss function that combines subcon with a class conditional info and CE loss, can induce spread. And we bypass the problems by constructing a distribution that is neither collapsed nor uniform, and analyzing its loss, and we introduce S, which is a notion of class variance, to measure spread on this distribution. We show that this distribution has an intermediate degree of spread by deriving bounds for the weights alpha and the class conditional info and CE loss, within which this distribution attains lower loss than either extreme. The second challenge is breaking permutation invariance. Our first result demonstrates that L of spread can induce spread but does not give the insight on class fixing permutation invariance. And this motivates the question that how should we break class fixing permutation invariance? We show that inducing an inductive bias towards clustering of latent subclasses can break permutation invariance, and more importantly, can result in good course to find transfer performance. And a standard approach to controlling this sigma is assuming Lipschitzness of the model. But the Lipschitzness is a strong assumption for modern deep networks, which are powerful enough to memorize random noise. In empirical measurements, we find that modern deep networks display poor Lipschitzness, and thus a Lipschitzness assumption is insufficient for inducing clustered subclass representations. We thus propose two alternatives that can bound sigma under more realistic assumptions, directly encoding fine-grained details by concatenating the representation from a class conditional autoencoder and using data augmentation in the class conditional info and CE loss. So we have a deterministic class where y, and so we assume the data is class balance. I mean, it is fair, all of them have equal chance. But data points also belong to latent subclasses, and we denote a subclass as a latent discrete variable that can be partitioned into disjoint subsets. And we have a class balanced labeled training dataset where points are drawn from identically independently distribution, and the value of each z sub I is unknown during training. And then we go from coarse to fine transfer. It evaluates how well an embedding trained and coarse classes distinguishes fine classes. Just fix a y and make suppose that sy is just z and z prime. The task is to classify z versus z prime using the encoder learned on that distribution. We are given a dataset of subclass labels, and this is all x that are equal to z. So we learn linear weights and construct an estimate by using softmax score. But f here is fixed because it's given f, then what is the probability of z? And then we can evaluate the performance of coarse to fine transfer with this gamma margin loss. But it could be considered as a modified supervised contrastive loss. And here B is a batch of data, and then PIB is all x that their edge are equal. And then we can define this spread loss, which is a linear combination of info and CE loss and the supervised loss. For example, for the supervised loss, or in the info and CE loss is the classic approach, and then we add them so that it's a trade-off between these two different objectives. But we make several standard theoretical assumptions restrict the encoder's output space to be on the unit hypersphere. So we have class collapse distribution and class uniform distribution. So they can prove that subcan's coarse to fine error is at least this one. So this is a lower bound for that. And we can define the loss of spread as a linear combination of alignment, augmentation, difference, and the same that are defined here. But the proposition is that align and augmentation are minimized when their f are equal, and L is minimized when mu is delta, and L same is minimized when mu is this sigma d minus 1. So there is an upper bound So it minimizes the spread, but with this upper bound. So we also have an upper bound for loss of spread. What is class fixing permutation invariance? So F is just a class of encoders, and L is the loss function over an encoder and a set of endpoints. We can define S as the set of class fixing permutations which satisfies, their H is equal, and then L is invariant on class fixing permutations. And this proposition said that L of spread is invariant on class fixing permutations. Inducing an inductive bias can break permutation invariance. So we define some additional terms. Let Y denote the class label corresponding to Z and Z prime, and define a quantity which is called delta of Z and Z prime, because we need the notion of separation between Z and Z prime. And then delta is large when there is a spread. So with probability 1 minus delta, the course to find error is upper bounded by this amount. We analyze 3 mechanisms on F for inducing an inductive bias that can cluster subclasses: a constraint encoder, a class conditional encoder, and the third one is data augmentation. But these 3 mechanisms use Lipschitz assumptions of varying strengths to that bound.